Thank you for joining me here today. I hope you're going to enjoy the webinar. We're here to talk about acceptance testing. But please make sure that you do subscribe to the channel if you haven't already, and hit the like button on the video. It really does help the channel with the YouTube algorithm. Thank you. Before we get into the main body of the presentation, I recently released a book called Continuous Delivery Pipelines, and last week it hit the top of the approval ratings of sales in LeanPub, which was delightful, of course. It's available for $19.99, and I'll leave a link in the description below. So if you're interested in that and reading it, do take a look. So let's move on to the actual content of today's webinar. We're going to talk for about I'm going to talk for about half an hour discussing acceptance testing, and then we'll go on. I'll do a brief sales pitch to you, talking about my training courses and stuff, and then we'll go on to a Q&A. So what is it that we're talking about when we're thinking about and talking about acceptance testing? And the first thing to say is probably that what we're not talking about is manual regression testing. We're not talking about that kind of human sign-off of work. In general, we don't want human beings doing regression testing. They're too slow, too inefficient, too low quality overall. They're kind of not repeatable and reliable. So we want to use the machines for that. And so in a continuous delivery sense, when we're talking about acceptance testing, what we're really describing is automated testing, but from the perspective of a user of the system. We're trying to evaluate the system in lifelike scenarios from the perspective of a user. So we want to assert that the code does what our users want of our system does what our users want of it. Another great boon in acceptance testing, if we get it right, if we're able to capture the desirable intent of our software in the form of an automated test of some kind, and we do that before we start, and then we can start work underneath that, doing test-driven development or whatever else beneath the surface of that, designing our software until that automated specification is met, then we kind of have this automated definition of done, which is a great boon to a development process to drive good practice in terms of building the right thing and not over engineering on solutions and so on. It gives us a target to aim for that is clearly defined. We want to also assert that the code works in a production-like test environment. We want to evaluate its configuration, the deployment of the system, to test that those things are correct too at the point at which we go into production. And we want to get all of these things, feedback on all of these ideas quickly and efficiently. And we want to find out just in time that this is broken rather than just too late, like this chap. The next idea that this leads into, I think, is the idea of acceptance tests as executable specifications for the behavior of our system. What we'd like to be able to do is to try and capture the behavioral intent of our software, specifically from the perspective of a consumer of that software, whatever that means, and create a specification for that behavior. That then allows us to do this thing of having this automated definition of done. It kind of teaches us, thinking of these things as specifications, it teaches us to that you write a specification before you start work, not after you've finished. So I think a specification is a better word than test, and specifically thinking about what it takes to specify the behavioral intent of your software. And that's really what we're trying to capture with these kinds of tests. The next question that tends to crop up here, and the pitfall that so many organizations and teams have fallen into over the years, is to try and allocate this task to a different bunch of people. Having is a kind of toxic anti-pattern that people have been trying to apply for decades. And I've seen people doing this, attempting to do this for the last 30 years or so, and I've never really seen anybody succeed. It just doesn't work. This isn't the way in which you approach this problem. And I think it's fairly obvious. If you start thinking of these things in terms of specifications, then it's clear that if our code doesn't meet its specification, that's not a problem that can be fixed by people writing the test. That's a problem that must be fixed by people developing the code. So I think the rest of these bullets are correct. Anyone can write the test. It doesn't matter who starts out writing the test. Having a QA team to help you write good specifications is not a bad idea. It works very well as long as they are collaborating very closely with the development team. Having a developer write the specification is absolutely fine too, or a product owner, or anybody else that clearly understands what the software needs to achieve. But as soon as that specification exists and people start using it to develop software, developers, then they are the people that will break the tests. Therefore, developers will own the responsibility to keep them working. So, developers own acceptance tests. It's their responsibility to keep them passing. It's their responsibility to make a correction if an acceptance test fails. It's not somebody else's responsibility. This closes an essential feedback loop in the development approach. And however hard you try, you can't hand this responsibility sensibly on to somebody else. The other thing that you kind of want to do is think about it. At the point at which I commit a change that breaks everything, what you really want to do is that you want to slow me down a bit and get me to help you fix whatever went wrong. And so developers being in this loop, being able to witness quickly and efficiently that they have caused a breakage, a test failure, a mismatch of specification through one of these tests failings, they want to be able to spot that quickly and efficiently. I would argue try and do that in under an hour. And then they're going to react to that. They're going to jump on that problem and they're going to try and address it. The next crucial idea to allow these specifications to work as specifications really is that what we're trying to achieve is to separate very clearly what the system does from how it achieves that. And this is a key idea. Here we have a diagram of a system, and we have a bunch of users kind of represented by the pale grey blocks at the top of the picture, UI traders, API traders, and so on. And they're interacting with the system through a variety of different channels. So through a public website, through a trading API, through other mechanisms. The detail doesn't really matter. If we were going to write automated acceptance tests to test these behaviors, what most people try to do is this. They'll write the tests, and most test cases of this kind that I see conflate the ideas of what the system needs to do with how it actually does it. So we'll write a test case that understands the ideas that we want to test, but also includes all of the details of how you connect and interact with the system under test to evaluate it. Now, there's a problem with this approach. Let's imagine that some part of our system changes. It doesn't really matter what. And that invalidates a bunch of these test cases as a result. Now, in order to fix that problem, we've got to go test case by test case and correct it. So there's a duplication of effort. Also, each of these test cases is going to be much more complicated than it needs to be because it's conflating the two ideas of what the system does with how it does it. We know how to cure this kind of problem in general in software design and software development, and you do this by introducing a level of indirection and raising the level of abstraction. And so what we're going to do is that we're going to try and capture the interactions with the system under test in the form of some kind of higher level, more abstract representation of the problem. The test cases then talk in that language and interact with it. So if, for example, we wanted to place an order for something, the test case would talk in terms of placing an order and maybe the details of the order, but they would say nothing at all about how to connect to the system in order to achieve that. That would be hidden behind this layer, currently color-coded green and red in the diagram, and that gives us an advantage. Now, what that means is that if we make a change in the system under test and that invalidates the same bunch of tests as before, we can now go and correct that problem in one place. So we can go to, in this case, the fix API, change the plumbing in the fix API, and that fixes all of the test cases. This is important, and this is a step forward. What I'm talking about here is really the creation of some kind of language that allows us to express the ideas in the test case without talking about how the system works. As you start digging into this kind of problem, what we tend to find is that there's a bunch of ideas that tend to crop up, and we can start thinking about this plumbing that makes it easy for us to write these test cases as a system in its own right, the test infrastructure. And that is most effectively organized as a domain-specific language, a language that is computable, executable, but allows us to express ideas in the problem domain in a way that we can capture our behavioral intent of the system without worrying about how the system works. And that's what I'm going to be talking about today. The next idea that is really central in trying to achieve this kind of ability to test these things is test isolation. The other aspect that is important to us in being able to evaluate our software with acceptance tests is we want them to be efficient. We want to be able to run lots of these tests, and as our system grows in complexity, we're going to have an ever increasing body of tests that we want to run to give us great feedback on the quality of our work and its match with a behavioral match with our users' needs. So thinking and taking seriously the idea of test isolation is part of that game to allow us to do things like run tests in parallel and scope tests appropriately and so on. I think there are 3 levels of test isolation to consider. This is the first one. This is the idea of test isolation in the sense that what is the boundary of your testing? What should be the boundary of your testing for a system? So in this example, let's imagine that we are working on system B, and system B is in a larger network of other systems and interacts with them in different ways, and it's kind of downstream from system A and upstream from system C. It's independently deployed, but you know, it's in a big organization with lots of other systems around it and connected to it. In this kind of scenario, what organizations often say is that we must do this. We must do end-to-end testing of everything together. People talk about things like staging environments and end-to-end testing and all these kinds of patterns where we're going to put everything together and evaluate it all. Now, there's a drawback with that strategy, and that drawback is that if we are testing in an end-to-end scenario, we don't really have control of the interactions to our system. We also can't very accurately correct the results that our system generates. What this means is that if this is our only testing strategy, this very seriously limits the degree to which we can test our system. It also means that we've got to kind of have some kind of omniscience to understand everything about every other system that there is. There are all sorts of things that are just literally impossible for us to test. For example, imagine that we wanted to test the scenario where system A was broken in some way, was sending us garbage, or where system C wasn't available, and so how does our system react when we can't actually interact with system C? Those are valid scenarios, and if we want to build good software, those are the kinds of scenarios that we'd like to be able to test system B with. But if we've got the real versions of system A and C in place, we can't test those scenarios because those systems are in our way. It leaves our ability to precisely define the state of the system that we're interested in. It's kind of vague. It's not very precise. So our testing is going to be vague and not very precise. So this is something of an anti-pattern. This isn't a very effective way of organizing this kind of testing. So what we'd much prefer to do is something like this. We'd much prefer to have test cases right up to the edge of our system, not compromising the public boundaries of our system, but interacting through the real interfaces to our system. But now we can kind of put synthetic data into our system, get it into whatever state we want it to be in. We can verify the output. I have this kind of mental model of we're placing calipers around the system and we're very precisely measuring it to figure out what it's doing. That gives us a much stronger stance on our ability to test our system and what it's doing. Now, there's a reason why an organization with systems like this says we need to do end-to-end testing. And that reason is, what happens if these interface points change? What happens if system A changes the way that it talks to us, or system C changes its API that we're calling into in some way that compromises our ability to communicate? How do we test for that? Well, if we want to be able to do what I said, we want to be able to test to the boundaries of our system, and we want to be able to test to the boundaries of all of the other systems, presumably, then thinking again from the point of view of system B, we're on team B, so what do we want? Well, what we're interested in is all of the weird edge cases that we want to test and normal behaviors and so on with our set of test cases. That's the bulk of our testing. What we are interested in terms of systems A and C is, does A talk to us in the way in which we expect? And do we get to talk to C in the way in which we expect? That means that we could write tests just focused on evaluating that. And when we do that, the amount of testing that we need to do just to verify that they can talk to us shrinks quite considerably. We're just testing that the interface hasn't changed in a way that we care about. This is called contract-based testing, and this is an effective strategy of defending system B from changing system A, or at least alerting system B if there is a detrimental change in the systems that it connects to. This is a very effective strategy, and it will give you a warning when there's a problem. Particularly if you're connecting to the test environments of these things as they're being built. There's one step further that's useful when scaling this up for a big organization, and that is that we're on team B, we write our tests that say we expect system A to talk to us like this. We then give those tests to team A and they run them as part of their deployment pipeline. Now, if team A or team C makes a change to their system that invalidates our assumptions of their interaction with us, the test will fail. And now they know that they've caused a problem, and they can decide what to do about it. Maybe they just, oh, we didn't mean to do that. They could modify their change so that it doesn't compromise the interface. Or maybe they come and talk to us and say, look, we've got a breaking change coming through. You're going to have to update, or whatever it is that we decide to do. But they've got the choice to and the visibility to manage that sensibly now. This is a much more scalable approach to testing than trying to test everything end to end, and ultimately gives us much deeper insight to our code. I said that there were two other levels of isolation that I think are important to care about. One of them is the ability to be able to run tests, multiple tests in parallel with one another in the same version of the application. If we want to be genuinely efficient, It would be great if we could start the application up once and then run a whole bunch of test cases in parallel, not caring which test cases were running alongside one another, and get results more efficiently back from our system. That would share out the cost of deploying and starting up the application between a whole bunch of tests. So that would be more efficient. So that's one form of approach. And the best way to do that is to kind of use what I call functional isolation. You use the functions of the application to isolate tests from one another. So every test, let's imagine that we were testing Amazon. Every test would create a new book and add it to be bought, and then you'd test all of the things about buying that book. So only that test would ever see that version of that book. So use the natural function of the system. The other thing that you build on top of that is this one, the temporal isolation. This is the idea that we should be able to run the same test over and over again in the same version of the system and get the same results every time. And this demonstrates the idea that I've just described in even more detail. So let's just walk through a little made-up test case to explore that. So here's a test that I wrote, and this is testing a library. So a bookstore. So here we're going to create a book called Continuous Delivery, and then we're going to place an order for the book, and then we're going to check that the order was indeed placed. The interesting part from our point of view here is this line here, where we create the book. What happens the first time that we run this? We're going to run this, and somewhere or other in the guts of our system, there's a data store of some kind or other. And when we say create a book, we're actually going to create a book that we can kind of search for and find and place an order for in the next part of the test. And if we just do the simple thing of saying, okay, the test said create a book called Continuous Delivery, so we create a book called Continuous Delivery, that creates a problem because the next time we run the test, we're not in the same state. There's now already a book called Continuous Delivery, and that version may have been changed in a test. Maybe we were testing something else that changed the price of the book, or how many were in stock, or whatever else. So it's going to make this test fragile because information will have leaked between this test and another. I've seen people do things like try and roll back transactions at the end of every test, so anything that's written to a database is lost and all that kind of stuff. It just adds complexity. I think there's a much simpler approach. So let's imagine that our test infrastructure is a little bit smart, and it says, when we say create a book, it says, aha, I know that you don't really care what the book's called, so you carry on calling it Continuous Delivery, and in the context of this test and only this one execution of this test, I will always make Continuous Delivery map to whatever it is that I create. But I'm going to create something else altogether. I'm going to create a book called Continuous Delivery 1, 2, 3, 4. And the next time you call create book, I'm going to create Continuous Delivery something else. And now these tests can run in parallel and not interact with each other in any way. By using this kind of name mangling within our test infrastructure, we get temporal and functional isolation that allows this test to be wholly independent of any other piece of code that interacts with the system that we're testing. I once did some work with Siemens Healthcare, building software that managed data from machines in hospitals, and for nearly every test that they created started off by create a hospital, and then create a whole bunch of machines in a hospital. So you can do some quite clever things in order to be able to get the system into just the state that you want it to be in order to be able to evaluate it. All of this stuff is made much easier if we start applying the language of the problem domain to capture these test cases. Here are two real-world examples from a trading system that I was involved in building, and both of these are in the language of the problem domain. So actually they're also in Java in this example. But if you look carefully about how the code here is organized, apart from the slightly weird camel case separation of words, and there's a few dots and brackets and curly braces and semicolons here and there. All of the words, all of the ideas are ideas from the problem domain. And I know this to be true because we did this. If you put a test like this in front of a human being who understands trading, they will be able to understand what this is doing. They will clearly be able to follow what's happening, the scenario that is captured here. It turns out that human beings are quite good at language parsing, even better than computers. And so if we put some of the work onto them, we can get away with this kind of halfway house between something that is absolutely a computable language, a computable grammar, but is also in the language of the problem domain, and so allowed to express ideas only in terms of how the system works. Now, actually, these two examples are leaking information a little bit about how the system works, and we got better at it over time. We ended up creating tests that looked a bit more like this. Now, this is wholly abstract. If you ignore the kind of the decoration of Java test cases and the channel annotation which we added, which I will explain in a moment, all of the rest of the words are language of the problem domain. Should successfully place an immediate or cancel by market order. If you said that to any trader, they'd absolutely understand the context of what was going on. They know what a buy, cancel market, an immediate or cancel by market order would be. And then we're placing an order, and there's the detail of the order, and then we're going to wait for a result, and there's the result that we should expect to see. The interesting part here from what we're talking about today is that channel annotation, though. What that is saying, that's the techie bit, that's the crossover. What that's saying is that this single test case could operate through the institutional trading API, which is what the fix API was, the deal ticket, which was what we called our web application front end. So the UI, the web UI, or the public trading API that we supplied for anybody to write bots against our system with. So this single test case could run through 3 completely independent channels of communication with our system. Think about what that means for a moment, and think about, you may not have this problem, you may not have this kind of multi-channel issue with your system, but think about what this means in terms of the separation between this test case and the system under test. This test case, this executable specification, is precise and accurate in the scenario that it is describing from a business point of view, but it says nothing at all about how the system under test works. This is powerful and valuable stuff. It means that the system under test can change without us invalidating this test case. These bits are the bits that are that need to change. What I'm describing here ultimately, and the kind of really the theme for my talk today, is this idea of this 4-layer structure for acceptance testing. At the top of this layered structure are our test cases captured in the way that I've described, captured in this domain-specific language that allows us to express ideas from the perspective of an external user of the system in the language of the problem domain, focusing only on what the system should do. Then, still in that space, is the DSL, the domain-specific language that is the common code that is shared between all of these different test cases. Ideas like placing an order and looking at the results and so on. This allows us to capture these behaviors, do the things like the test isolation, and do all of those in a generic way that still doesn't know how the system works. The next layer down, the protocol drivers, are the bit that does the translation. These are the bits that were being referred to in the channel annotation in the example that I just gave you. Effectively, what that channel annotation was doing was saying you can use these 3 protocol drivers. So run it once with protocol driver for the web UI, once with the protocol driver for the fix API, and once with the protocol driver for the public API. And then at the bottom is the system under test. So the protocol driver translates between a concept like place order into go to this URL, put this value into this field, this control, and this other value into this other control, and then press this button to place an order. Or go to, if you were doing this through an API, then build a message and, put this value into this field in the message and this other value into this other field of message, and then send this message to this destination. You can imagine writing drivers that do that kind of thing. This is a fantastic tool I've used in all sorts of fairly complicated testing scenarios. The next key idea to think about is the idea of controlling the variables. We want to be able to, a good example of that is testing with time. Time is one of those awkward variables that tends to run on behind our backs. So here's a made up example in this case, and we're going to a library and we're going to borrow a book called Continuous Delivery. I hope you're spotting the theme. In this case, we're going to assert that the book is not yet overdue, and then we're going to time travel forwards 1 week, and then we're going to assert that the book is still not overdue. Then we're going to time travel forwards a further 4 weeks, and we're going to assert that the book is now overdue. So the interesting parts in this example are clearly these time travel-y bits. So what's going on here? So if we've got a system that cares about time in this way, we're going to have somewhere or other, we're going to have a piece of code like this. Somewhere in the guts of our system, there's going to be a line of code that says something like system.getTime. And if this is all we've got, then, and we want to test our system through time-based scenarios, then all we can do is change the system clock, which is not a good idea because that system clock is involved in lots of other things. What we'd really like to do is to accurately control the variables. We'd like to control time, but only for our application that we're testing. So how could we do that? Well, instead of asking the system for the time, we can start by cheating again, and this time we're going to ask a clock that we create for the time. Now we can make the clock lie on our behalf when we're testing. So we could create a clock that by default just goes through and asks the system for the time as before, but also gives us the opportunity for something else to tell it what time to report. Now we connect that up with some plumbing to our test infrastructure, and when our test case says time travel forwards a week, we're going to, our DSL is going to do something, say, well, this millisecond is right now, and a week is so many milliseconds. So adding so many milliseconds to now, that tells me what time we're supposed to be reporting, and I'm going to send that time to the clock. So we can do that kind of thing. Now we're starting to get fairly sophisticated in our interaction with the systems and the kinds of things that we can do, the level of control that we can exert on our system. And one of those things is we start worrying about how these different kinds of tests may interact with one another. So time travel tests are a great example of that. So imagine, running two different time travel tests in the same version of the system. The system is going to be pretty schizophrenic and being quite a mess. So we ideally, for a time travel test, we probably want to isolate that and only run that in one reserved version of the system for it to be able to do. And similarly for destructive testing or testing that depends on a particular piece of hardware. So we could imagine annotating our tests with tags that are going to inform something else what to do. Now we can start imagining a piece of software that, when we're executing our tests, reads these annotations and decides what to do with them. Here's a little animation which was generated by my friend Mark Price when we worked together, and this is a fairly early version. It got more complicated than this, but showing the allocation of test cases in our test grid. On the right hand side at the top right where it says parallel, what that is showing is one version of the application at the hub of all of those tests, and the pale green dots surrounding it are different test hosts running different tests against that shared version of the application. On the left hand side are the time travel tests. Each of these is allocated a new version of the application, so it can time travel to its heart's content without interacting adversely with any other test cases. This is really powerful. This gives us an awful lot of flexibility to play with the tests and control the variables and get consistent, repeatable results. That's the end of my presentation, and we're going to go to the Q&A very, very shortly. Before we do, I just want to do a little bit of reporting, and I've got a little bit of news for people watching. So I've developed a collection of self-paced online courses. And excuse me, I'm just changing the screen. There we are, that's better. And these go deeper into the topics that we're describing here. Today, I'm announcing the release of the latest course in this series, and it's now open for enrollment. It's called Get Going with Continuous Delivery Pipelines, and it kind of complements my book that I mentioned earlier. In it, you learn the fundamental skills that are at the core of continuous delivery and DevOps, and it's at an affordable price. So it's well worth taking a moment to check it out. Again, I'll leave a link in the description below. If you choose to go deeper beyond this course into understanding these practices and skills, there's an option to take on the more advanced Anatomy of a Deployment Pipeline course. If you do so, you should choose to take that step up. Then you'll get your £99 back, the enrolment fee from the Get Going course. So it's a great way to start and figure out whether the courses work for you. If you've enjoyed this webinar, you can keep up to date with more online events. Excuse me, that didn't work. Right. If you've enjoyed this webinar, you can keep up to date with more online events like this by joining my mailing list. You'll also get access to exclusive content that's available only to mail list subscribers. For example, when you join via the link in the description, you'll get your first how-to guide on assessing your continuous delivery capability. Finally, if you're looking to learn more about the stuff presented in this webinar, keep an eye open for the continuous delivery training site, as the next course that we will release will go deeper into these concepts. We expect to release this in the next 2 to 3 months. So join the mail list, and we'll keep you informed. There's a link and details in the description below. Right, onto the Q&A section. Let me look first at what messages we've got, what questions we've got. Question from Bulat. Hi Dave, would you please share your thoughts on Git flow approach? I kind of have a video on this on my on the channel, talking about the difference between feature branching and not. Git flow is a feature branching approach really, and I have a bit of a problem with that as a continuous delivery person. I think that continuous integration, which is at the heart of, one of the practices at the heart of continuous delivery, is important. And what it does is it's based on trying to frequently get high quality feedback on our changes. The original idea of continuous integration was expressed by the inventors as, imagine if you made a small change and that change was instantly available to everybody else working in the same code base. And so we're trying to get as close to continuous as we can. Branching of any form is about isolating change, and so is not really continuous. It doesn't really give us that that flow of feedback that we're looking for. Just as an example, if we are working on the same team and we are each working on a separate branch and we don't merge that branch to trunk until we've finished, then that means, even if we're pulling changes from trunk all of the time, it means that we are blind to what the other person is doing. There's some data on this, and the data from the State of DevOps report says that teams that merge to trunk at least once per day, which is part of the definition of continuous integration, produce higher quality software, more efficiently. So, so I think that there's the Git flow puts some barriers up to our ability to get that insight into change. We want to instead work in a way of making changes. Now, the compromise that comes with continuous integration, that kind of works against the Git flow model, which is based on having waiting until a feature is complete until you put it onto some form of release branch. The problem with that model is that you lose continuous integration and this visibility. The problem with the continuous integration model is that if we buy into the description that I gave you, we're going to make many small commits. We're going to evaluate those commits to the point where they are releasable into production if we work in a continuous delivery scenario. What that means is that we've got to be comfortable with the idea that any one of those changes could go into production, even if the feature is not finished. So we've got to start to change the way that we work so that we're able to make changes that don't yet add up to a complete feature, but still could be deployed into production. And there are some techniques. I have a video on the channel which is talking about feature branching and continuous integration that goes into some of the strategies, which are primarily dark launching, feature flags, branch by abstraction. Those are the techniques that we use to allow us to work in these little drips. But I'm a continuous integration person, so I think that's a significantly more effective strategy than working on separate branches. And so I will be. I would advise you. I would advise you not to work in Git flow. I'd advise you to work on trunk-based development, continuous integration, whatever you want to call it, committing frequently, multiple times per day. My preferred working approach is that I'm going to do test-driven development. I'm going to do red-green refactor. And after I've refactored, I commit the change. So if I'm working well, I'm probably committing to the releasable line of my code, trunk, master, origin, master, whatever you want to call it. I'm probably committing to that line of changes every 10 or 15 minutes. And so getting feedback. Does my change work with your change every 10 or 15 minutes? Next question. I'd like to know how, this is from Caesar, or Cesar, I'm not sure how you pronounce it, I'm sorry. I would like to know how acceptance testing converts with client acceptance. You're probably not going to be able to convince your clients to drop their version of acceptance testing. My preferred approach to training them to want to drop it themselves is to create software that they find so few bugs in that they realize themselves that it's a waste of time. Let me tell you a little war story. When we built our financial exchange, the product owners and the rest of the business decided that they should be involved in the release process. We built our exchange from scratch, having adopted continuous delivery as our approach from the day one, and so our deployment pipeline gave a pretty definitive statement on whether this thing was releasable. We were running, by the time I left, we were running somewhere between 60 and 100,000 tests of all different kinds within our deployment pipeline, getting an answer back in under an hour. So we knew that the software worked. We knew that it did what the users wanted it to do because our development was organized around the executable specifications that I've described here today. So we knew all that worked. So by the time we released, we weren't worried about whether the system would behave functionally or not. And so we would release it into production, all automated, and we used to release on a Saturday. And the product owners and some other members of the business would go and play with it for a bit. They'd go and tinker with it for a bit to acceptance test it, to make sure that it was okay for release on the public. After doing that for about 3 months, it didn't affect us. It didn't change anything. They never found anything wrong with it because our automation was good enough to do that. So after about 3 months, they came to us one day and they said, would you mind if we didn't do that acceptance testing anymore? Because we quite like Saturdays and we've got better things to do on a Saturday than test your bloody software, which we never find anything wrong with it this way. So we said, no, that's fine. So they dropped it. So that's a good strategy. So over deliver so that they're not going to worry about it. You're not going to be able to force it on them because they won't trust you. They won't, and probably justifiably, because we've kind of burnt the trust over the years of producing software that wasn't good enough quality to be able to do that kind of thing, to make that kind of promise. So you've got to have a really good statement on your automated testing to be in that situation. But what I've described is kind of part of that approach. So my goal with adopting this kind of approach in a team is to make the need of human sign-off acceptance testing kind of redundant. That's what I'm shooting for. But I'm probably not going to start off by stating that to the people that want to do it. You do want to remove any internal manual testing. You do want to remove any, regression testing, manual regression testing, because it's too slow. It's too low quality. It's too inefficient. It's too expensive. Spend that time, effort, and money on doing a better job of automating testing, and you're going to get an awful much better return on your investment. And then if your consumers want to do some kind of sign-off process, fine. If you're working at a standard where they very rarely find anything, they're going to get bored eventually. So I would tend to take that kind of approach. It's a bit hardline, I accept, and it does depend on lots more going on in the testing. But I think that's viable. It works out okay. Somebody said, "Can we have the webinar slides?" We will be publishing this on YouTube, so you can certainly watch the slides on YouTube almost as soon as this video is finished. We'll publish it at the usual time for the channel, which is 7 p.m. Just give us a little bit of tinkering time. Somebody else asking, will it be published on YouTube? And do developers, from Jim, do developers own the tests, or do developers own the implementation that verifies the acceptance tests? I think there's a distinction. I think that's a good question. I tend to think of it as the developers own the tests. One of the things that I didn't talk about today is the way in which you develop these tests. I said that at the outset that anybody could write the test cases, whoever understands the problem clearly. And the way that I've done it in many organizations, but the first time was at LMAX when we built our exchange. The way that we did it was that usually it was a QA person, often pairing with a developer who wrote the first version of the test cases. The developers would own the implementation. So the developers would own the implementation of the DSL and the protocol drivers. At the time of writing, the QA team probably, you could think of, mostly owned the specification itself in the test case itself. But then as soon as we started using it, the development team owned the responsibility for it. The key part, the part that really matters, I think, is that the development team own the plumbing part. So they keep the protocol drivers up to date, and they do that in reaction to test failures on the whole, or the addition of new behavior that wasn't added before. That approach allows the DSL and the plumbing for the DSL to grow kind of organically. You don't have to start out by writing a whole DSL that covers your whole problem space. You start off with one single test case and write the plumbing in the structure, the 4-layer structure that I've described, the kind of thin sliver of that behavior, and that works really nicely. From Helvanic, what do you mean by testing these interfaces as contract-based testing? For example, an API, do you limit your test to routes, validation, or the whole response? How far do you go? This is an interesting question. What's an API? And I think that what's an API is, the functions that you call, the messages that you send, all that sort of stuff. But the detail as well, the data structures that travel through, that's part of the API too. And so you want to test that stuff. So I'm not saying test as a black these things. I suppose I am saying test them as a black box, but you want to test the API to the degree that you are testing, the data that matters. So if you, let's say for argument's sake, that our service B, accepts a message from service A, and we are only interested in a couple of fields in that message. We're not interested in all of the stuff that's in that message. Then we only need to test that it sends us those fields. The rest of the message can change it any way it likes, and it's not going to affect us. So we test that. If our code depends on everything in the message, then we test that nothing has changed in that representation in a way that's going to impact us. There's another facet to this. If you're designing, architecting a system to be decoupled, you certainly want to build some defenses into your system. So you want to translate those sorts of inputs into your service. That's one of my bits of advice is people that do microservices, which are supposed to be independently deployable. Another video on the channel that you should check out if you haven't seen it. These things should be independently deployable, and that means that you want to put a little bit of wiggle room. You want to put a little bit of insulation between other things changing and you having to respond to that change. So I would argue that you should always translate the inputs to a microservice at the point at which you receive them into some form. That ought to give you the facility to have a change that is easy to fix. You just fix the translation layer without going in and changing all of the logic behind it. And that's a much nicer kind of way of designing those sorts of things. It's commonly referred to as kind of ports and adapters pattern. So I'd certainly apply that kind of approach, that kind of thinking, to be able to do that kind of thing. So what do you test in the API? The stuff that's likely to break you. But just plugging that into an end-to-end system isn't better, because that's just a sample of the behaviors of that system. It's not really exercising that interface to any great degree, and so it's just a sampling exercise, and it's a very limited sampling exercise. I would argue that if you take testing seriously and contract testing seriously, you more thoroughly test those interfaces than if you do conventional end-to-end testing, which is usually a replay of generally fairly dull scenarios through the application. And the times when your application breaks is usually not the dull bits, it's usually when things get exciting in the wrong kind of way. From Ricardo, that test isolation idea is not the same as mock stubs used in unit tests, but elevated from unit to acceptance. It kind of is. So the first thing, the starting point, the way in which you evaluate your system, a deployable unit of software in a deployment pipeline with these kinds of acceptance tests that does talk to external systems, is that you fake those external systems. Now, these are not going to be simplistic kind of mock library style fakes. They're going to be more complex than that, and you want to programmatically interact with them from your test infrastructure. So you're going to build back channels to them so that you can kind of inject fake data from that from that source, or collect results from that source so that you can evaluate it. So you certainly want to be doing that kind of thing. But I think that the idea is the same. I think what we're trying to do is that we're trying to draw a boundary around the piece of code that we want to evaluate, in this case, a deployable system. And then we want to complete, as far as we're able, we want to completely control that. So we're going to give that piece of code the illusion that it's working in the real world by faking its inputs and collecting its outputs, so that we can evaluate it. That allows us to control the variables much more thoroughly and get a much cleaner picture of what's going on with that piece of code. From Inga, in reference to test isolation, the book's creation still needs to be tested, right? maybe we can randomize the input data. Sure. So this isn't the only test. So that's just one example. So in it, let's imagine that we were testing Amazon, then quite a lot of testing Amazon is going to be about books. And so being able to place a book to start off with is where we're going to begin. Certainly, there's going to be a test somewhere else that's about testing the creation of a book, and it's going to be much more thorough, much more detailed, but we're going to encapsulate that learning in this test case. And our create book instruction in our DSL is not going to allow us to proceed unless the book was successfully created. So that gives us a robust, repeatable approach to creating a book in order to be able to create a test case. What that means is that there are some behaviors of the system, like in this example, creating a book, that are going to be effectively tested in nearly every test case in the system. But that doesn't really matter. That's just about getting the system into the state that we want it to be in order to evaluate it. From Jean-Baptiste, do you make specific build to inject the controllable clock? Does it mean that the tested build is different from the one you're going into production, or production build has a controllable clock? My preference is probably the second one, if I can do that without compromising security in any way. So this is one of, in general, I really quite dislike to break encapsulation to support testing. And this is kind of doing that, really. But time is such a special case and such a difficult case in general for systems that I think it's probably worthwhile in this very narrow circumstance. I wouldn't do this, for example, for a database or something like that. But for time, this gives me the opportunity to do testing that I wouldn't otherwise be able to achieve. So what I'm going to try and do is that I'm going to try and engineer this in a way so that I am still testing my production code, but in a test environment, and only in a test environment, there is a route by which I can change the clock from testing. And that does have some security implications that you need to think about and consider, but it's not beyond credibility to do that. So when we did that for our financial exchange, there was physically no connection that was available to somebody from the outside world that would allow them to change the clock, because it was on a different the communication channel that allowed us to do that was on a different network to the one that was connected to the public access. So, but we had that separate network not just for time, but for any admin function of the system. So that's so that kind of secure communication only went on the admin network. So it's more secure. I've got a couple more questions, and we're rapidly running out of time, but I'll try and get to them. From Haymega, I've noticed some development teams prefer to run acceptance tests outside in using a real database, while others do subcutaneous tests in process, sometimes using an in-memory database. I don't think the ones in the in-memory database count as acceptance tests, because they're not testing the production system. They're not testing the deployment or the configuration of the whole system. So those are a different kind of tests. I've done those occasionally for certain kinds of features, but I wouldn't base my acceptance testing on those kinds of fake databases. If the real database is too slow to run your acceptance tests, too slow to establish, there's something else wrong, and I'll try and fix that instead. It's not a testing problem, it's a problem with the system. So I tend to look at that. The last question for today, from Roger. When working with feature flags, is there any tooling or framework that can help to write automated testing that covers not only the new features, but the old behavior that's being changed? None that I've used, and therefore none that I can recommend. I am a little bit cautious of feature flags. They are the last one in the arsenal that I will tend to pick. They're an incredibly valuable tool. Don't get me wrong. They are powerful, and there are times where you really should use them. But the problem that I have with feature flags for the kinds of systems that I tend to be involved in building is that which version do you test? And it's the question that you're asking. Which version do you test? Do you test it with the flags turned on or turned off in your deployment pipeline? And you might say, well, let's test both. Then we've got the ability to switch the feature flag. And at which point I say, well, okay, that's fine as long as you've got one flag. What if you've got 500? If you've got 500 flags, then the combinatorial explosion of pass through your code base with all those flags switched in different configurations is not really a testable surface area. And so that's a problem. So I tend to prefer to have fewer flags rather than many. Don't get me wrong, there are many organizations that are famously have hundreds of flags in production at the same time and seem to do fine with it. I'm just a little bit more cautious in the sorts of systems that I've worked on. And so I would be a little wary of using too many feature flags, and so that means I'm going to use dark launching and branch by abstraction first, and feature flags as last of the options that I choose to do. I will go through the comments in the stream afterwards, and I will try to write. I'll try and answer them in the comments. We are out of time, and I would like to thank everybody for attending the stream today. I hope you found it interesting and fun, if not useful. Of course, I hope that you find it useful. Thank you very much for your support of the channel, and I hope to see you here again soon. Thank you, and bye-bye.